Hello, in this video I'm going to solve the following problem for you. Evaluate the following integral. Integral dx over x times 1 plus x squared to the power of 3 over 2. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. If you do your calculations correctly, one possible answer that you will get is as follows. 1 over square root of 1 plus x squared plus 1/2 times ln of absolute value of 1 minus square root of 1 plus x squared all over 1 plus square root of 1 plus x squared plus a constant c. Okay, now let us solve the problem here. So seeing 1 plus x squared and this fractional power indicates that it's a good idea to use the trigonometric substitution. And because I have 1 plus x squared, that should be an inverse tangent function. So we introduce theta to be tangent inverse of x. This implies that tangent of theta is x, but also implies that theta is in the range of the tangent inverse function, which is from minus pi over 2 to pi over 2. So if theta is supposed to be tangent inverse of x, theta should be somewhere in the fourth or in the first quadrant between minus pi over 2 and pi over 2. Okay. In order to solve this, I have to get rid of my old variable and introduce my new variable inside my integral everywhere. So I need the x. So the derivative of tangent theta is secant theta squared d theta. So then I put them here. So my integral, if I call it I becomes equal to integral secant theta squared d theta. Instead of x, I put tangent theta, and then I will have 1 plus tangent theta squared to the power of 3 over 2. Okay, and then I have this formula. We know that 1 plus tangent theta squared is secant theta squared. Okay, so then I have this 1 plus tangent theta squared to the power of 3/2. It becomes secant theta to the power of 2 to the power of 3/2. Okay, and then it becomes absolute value of secant theta to the power of 3. Yes, so I just want to mention that this should be absolute value. For example, let us say that I have x to the power of 2 and then to the power of 3 over 2. If you just simply write it as x to power 3, this is not totally right. Why? For example, if x is minus 2, then what happens? The left-hand side becomes minus 2 to power 2, and then you have to the power of 3 over 2. But I have to do this operation first, so minus 2 to power 2 is 4, and then of course 4 to power 3 over 2 is indeed 8. But if I put minus 2 here, then it becomes minus 2 to power 3, and it becomes minus 8, so they are not equal. So this is valid if x is positive, but if x is negative, then that is not valid. So the correct form of it is to write absolute value of x to the power of 3. So that's the reason that when I wrote this, I didn't write secant theta to power 3, I just wrote absolute value of secant theta over 3. But of course, in this problem, it doesn't matter, because theta is somewhere in the fourth or in the first quadrant, and in those quadrants, cosine theta is positive, and secant theta is nothing except 1 over cosine theta. So this means that secant theta is positive, and then I can remove the absolute value sign. Okay? So, but I just want you to understand, you should be able to do it perfectly, it should do it precisely, because sometimes it matters. Sometimes when you remove the absolute value sign, you have to put the minus sign there, okay? So we don't need it, and I claim it here. Okay, so this becomes now equal to integral secant theta squared d theta tangent theta, and then this one is secant theta cubed. Okay, two of them and one of them are gone, so this becomes integral d theta, and then I have tan theta secant theta. Yes. So what can I do now? I can bring it up. Secant theta becomes cosine theta, and tangent theta becomes cotangent theta, which can be written as cosine theta over sine theta d theta. Okay, so then what do I have? I have this. So this becomes integral of cosine theta squared over sine theta d theta. Okay, then how can I solve this problem? For example, I can write it as 1 minus sine theta squared divided by sine theta, and then I have d theta. Then I can decompose this integral into two integrals, 1 over sine theta, and then I have d theta, and then I have minus this one divided by that one. One of the signs survives, and then you have this. But this is nothing except cosecant theta, so this becomes integral of cosecant theta d theta, minus that integral is simple, it becomes minus cosine theta, and then of course I have my constant c here. But this one is also famous, so it becomes, so if you don't mind, let me write cosine theta first. The answer to this integral is minus ln of absolute value of cosecant theta plus cotangent theta, and then finally plus the constant c. So you see integration is finished here, but I have to switch back to my old variable x. So what can I do? I have to write cosine theta, cosecant theta, and cotangent theta in terms of x. But x is tangent theta. Okay, so I will do this. I can use this formula once more. So 1 plus tangent theta squared, tangent theta is x, so it becomes x squared, is equal to secant theta squared, but secant is 1 over cosine, so it becomes 1 over cosine theta to the power of 2. So this means that cosine theta is 1 over 1 plus x squared, cosine theta squared, and then I take the absolute value, take the square root, it becomes absolute value of cosine, but this one becomes 1 over square root of 1 plus x squared. But I don't need the absolute value sign for the same reason, because theta is somewhere between minus pi over 2 and pi over 2, and cosine is positive there. So this means cosine theta is exactly 1 over square root of 1 plus x squared. Okay, so in the book, sometimes they use this. So they say that, okay, let us try a triangle here. So tangent theta is equal to x. So let us take this theta, and then you can interpret this as x over 1, but tangent is the opposite side, you call it x, divided by the adjacent side, you call it 1, so that it becomes consistent with that condition of tangent theta to be x, opposite divided by the adjacent, and then you read the hypotenuse using the Pythagoras theorem, which is of course this one, and then you say that, okay, I need cosine theta, so cosine theta is the adjacent side divided by hypotenuse. The reason that I don't like it, because when you draw the triangle and put theta there, you are implicitly assuming that theta is actually an acute angle, is an angle between 0 and pi over 2. But there is nothing to force us to believe that, yes? Because if I ask you what is the domain of this function that I am integrating, the domain of this function is every x except 0. Okay? If x is every number except 0, there is no guarantee that theta is an acute angle. Yes? Because, for example, if x is negative, theta cannot be an angle between 0 and pi over 2. So, even though this works here, but I don't like this that much because that is not very precise. You are implicitly assuming that theta should be an acute angle, and you don't have any reason to believe that. Okay, this is why I prefer this way, and I really want to emphasize on the intervals on which these theta lives. Okay, so let us go here. So what about cosecant theta? So cosecant theta is 1 over sine theta, but sine theta can also be calculated, yes? So for example, this is my cosine theta. So sine theta is cosine theta times tangent theta. Of course, if you want to use trigonometry. If you are more comfortable doing it, it's clear from this picture that sine theta should be the opposite side divided by the hypotenuse. So that is what you get from this analysis, which is of course true in this case. So here, if I want to use this formula, so cosine theta is that expression, theta, tangent theta is x. So if I multiply cosine by tangent, I will get exactly the same answer. Okay, but now you know that you need cosecant theta. Cosecant theta is the reciprocal of sine theta, so it means cosecant theta is square root of 1 plus x squared over x. So this is your cosecant theta. And if I ask you what is the cotangent theta, so the cotangent theta is 1 over tangent theta. The tangent theta is x, so cotangent theta is on 1 over x. So if I plug everything back, finally I get an answer. So the integral that I'm looking for is what? Is instead of cosine theta, I put this expression, 1 over square root of x squared plus 1, or 1 plus x squared, doesn't matter. And then I have minus ln of absolute value. Instead of cosecant theta, I can put this expression, and instead of cotangent theta, I can put this expression, but you see the denominators are the same. So if you don't mind, let me write the common denominator, and then I have square root of 1 plus x squared, and then plus 1. I don't know. This answer seems simpler than the one given in the book. If you look back here, so the first term is exactly what we got there. But for the second term, we're supposed to get this one, okay? I would say that the answer that I got here is simpler in form, but if we want to convince ourselves that this answer is also the same, so let me try to convince you about that. So I will start manipulating this algebraically a little bit so that I can convince you it is either the exact expression that I got on the board, or it differs by at most an additive constant. Okay, so let us go on the board. So this is the expression. It's 1 over 2 with positive sign, of course, and ln of absolute value of 1 minus the square root of 1 plus x squared divided by 1 plus the square root of, yes, 1 plus x squared. Okay, so what we do here, I would write it as 1 over 2 ln of, so I multiply the numerator and the denominator by the conjugate of the numerator. So it's minus 1 plus x squared over 1 plus the square root of 1 plus x squared, and I multiply it by 1 plus square root of 1 plus x squared divided by the same expression. Okay, so then what happens? This becomes equal to 1/2 ln of this one times that one. It becomes that expression to power 2. Yes. And then this one times that one is the conjugate rule. So it becomes the first one squared minus the second one squared. But now let us continue. This becomes 1/2 ln of, if I open it up, 1 and 1 are gone, so I will have minus x squared here, divided by 1 plus square root of 1 plus x squared to the power of 2. Okay? So now this absolute value sign cancels this minus sign, and I can write it in this form. So it becomes 1 over 2 ln of absolute value of x over 1 plus square root of 1 plus x squared, totally to power 2. But then this 2 will go to the back, will cancel this 1/2. It becomes ln of absolute value of x over square root of 1 plus the square root of 1 plus x squared. But you know that if I flip these two, there will be a minus sign coming out. So it becomes minus ln of square root 1 plus the square root of x squared over x absolute value. Okay, so I was able to show that this minus ln of this expression, as you see here, is exactly equal to the one given in the book. So I don't know, for some reason, why the book, might be the way that I calculated this is different, but I would prefer to keep this because this is simpler in form than this one. Anyway, we haven't done something wrong. At least that's good news. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.